Good morning, everyone. Thank you for being present here for this talk. So the talk is titled Far-Field Speech Recognition Using Multivariate Autoregressive Models. And I'm going to present, I'm Sriram Ganapathy, and the co-author who is now in Carnegie Mellon University is Madhumita Harish. So the roadmap for the talk is the following. So what I will try to do is to motivate the reason why research in this direction is important and why we need to work on signal processing and machine learning models in parallel to improve the state of the art in speech recognition in far-field environments. I'll talk about a little bit of the relevant work. Some of it was during my PhD days and sort of relevant prior work in this direction. And we'll go into the details of the proposed model that is the part of this paper. We'll highlight some of the experiments and results that were done for this paper and try to give a brief conclusion. So the motivation, automatic speech recognition in far-field environments is still very challenging, and a lot of sessions, poster and oral sessions as well as talks have highlighted this importance of working in far-field environments. It is certainly far from being solved. And here I have one of the best state-of-the-art hybrid system that was applied for far-field speech recognition. This example is from Corpus. And what you see here is the ground truth and the ASR output are very different in the sense that sometimes you get, for some portions of meetings, you get more than 50% word error rate, at which point accuracies and error rates are almost the same. So these sort of difficulties arise even with the state-of-the-art recurrent models and language models and all the bells and whistles that can be put together in the ASR system. So some of these effects, for example, can be alleviated by using a beamforming method, where essentially you try to combine the data from multiple microphones and enhance the quality of the audio. And still, they are much worse than, say, dealing with clean close-talking conditions in terms of ASR word error rates. So the question that this talk tries to address is, can novel signal processing methods improve feature extraction for speech recognition? I know that the signal processing aspects of speech are somehow in a minority, but we still try to worry about the questions in terms of whether signal processing can indeed help any of the speech recognition feature extraction. So prior work on signal dereverberation, I would like to highlight a few of the techniques that are still popularly used. In fact, some of the challenges like KIME, most of the winning systems still keep using dereverberation methods like weighted prediction error. There are approaches of this kind where you don't work at the signal level, but you work on feature level by using a spectrogram of the reverberant speech and trying to map it to the spectrogram of the clean audio using sorts of autoencoder based approaches or other methods based on mask estimation methods where you estimate a clean mask by using both the pair of the clean and the noisy audio or the reverberant audio and try to estimate the mask that will eventually allow you to map the noisy or the reverberant audio to the clean data. And several other approaches in terms of computing the features itself without using any paired knowledge of the reverberation, just by dealing with the signal properties of the reverberant audio, for example, modulation filtering, where you can try to model and remove out, normalize some of the effects of reverberation are also being pursued. This talk is partly in line with the last presentation here on the last citation here on the modulation filtering, which is what the proposed model tries to expand on. So just a bit of relevant prior work for this paper, which I would like to begin with to expand to the current proposed model. So this some of the work started even before this Samuel Thomas and my group, when we were doing it in the Johns Hopkins. Some of this work was started by Mario Satinios and colleagues at EDAP and in Dan Ellis' group. So the model assumption is the following, that if we have a time domain sequence, X of n, and I do a linear prediction on the time domain sequence, which is well known, and in fact some of this was highlighted by Bishnu et al. In the first talk. The time domain sequence, a linear prediction gives you a set of coefficients which can be used to model the power spectrum of the signal. So the power spectrum is an all-pole model. The whole approach is called an autoregressive modeling approach in statistics. And if I want to use the duality properties of the signal, meaning that if I want to take the signal not in the time domain, but pre-process it to map it to a frequency domain representation, and then apply the standard linear prediction that we are well aware of for the last 40 years, what we would get now is not the power spectrum, but we would get the temporal envelope of the audio signal. So this is the model of the temporal envelope, and this whole approach where we try to do the linear prediction on the frequency domain is what we will refer to as the FDLP. So we also attempt to model not the direct temporal envelopes of the signal, but try to model the subbands of the speech. The way to, one easy way to get to the subbands is to take the DCT and window the DCT into subband DCT coefficients and apply the linear prediction on each of these subbands. To normalize the reverberation artifacts at that scenario, what we attempted was to normalize the first order effects of the reverberation by making the gain of the envelopes to 1. And this showed remarkable improvements for various far-field speech recognition experiments. So this talk, getting to the details of this talk in particular, what I'm trying to proceed further in terms of the modeling is to take this previous slide approach and expand it to look beyond modeling one single band at a time. So the question that is attempted is, can we try to model multiple bands together than treating each band individually as a stream that has to be processed? So we could rely on, for this case, on the same modeling paradigm of autoregressive modeling, we could rely on using multiple bands together into the autoregressive modeling framework as a nice theory in vector linear prediction and also in multivariate autoregressive modeling. Some of this is in fact highly used in econometrics and forecasting in financial signal processing. So the model has the shape which is given here. Let us say YQ is a series, a time series. It is a vector time series. It has a d-dimensional vector, and now you are trying to predict the YQ based on some of the past samples of the same vector. And the prediction coefficients, unlike in the scalar case, become matrices in this point. There is also the white noise vector, which is denoted by U sub Q. I'm not going to go into the details of the mathematical model, the derivation of the model, but I will just highlight how the solution is obtained, which is typically based on using the least squares approach. The main novelty of this work, which is not perhaps of much importance in economic forecasting, is to derive the envelopes out of the vector linear prediction model. So we could derive the coefficients using the standard approach of least squares, but the paper in detail talks about how we can convert the the matrix coefficient of linear prediction output into a set of envelopes. So at the end, it comes out by using similar approach to the scalar case, except that now we have to deal with matrices. And a multivariate autoregressive model filter will be a matrix which is denoted by H here, and the covariance matrix of the noise is similar to the role that the variance plays in the scalar case. Okay, so without going into the technical or the mathematical details, I would like to give more of an intuition of how the spectrogram computation happens in this case. So we start with a long time domain signal of the order of 2 seconds. We apply a DCT on this long temporal sequence. It's a real transform, and it's perfectly reconstructible from the DCT. Once we have the DCT coefficients, we apply a MEL-based subband windowing, which is to approximate the MEL spectral resolution. Out of the MEL spectral subband windows comes a set of DCT coefficients for each subband. Now we could start taking the subband windows of multiple subbands, assuming that each of them have the same length, and use those multiple subband DCT coefficients as a vector process, which can be modeled using the multivariate autoregressive model. So similar to the one-dimensional case, except that now we are dealing with multiple subbands, we approximate the subband envelopes. The advantage here is we find a good benefit by trying to model multiple bands in parallel than trying to model them with isolation. Once the subband envelopes are generated, what we will do is to try to take the average of the subband envelopes in each of the windows of 25 millisecond duration. So similar to what we were doing in the 1D FDLP case. And these envelope averages sort of represent like a spectrographic representation of the speech signal. to illustrate how this performs on a reverberation setup. This on the left-hand side, you have two plots, essentially plotting the spectrogram representation from standard MEL processing, as well as the MAR model that was described in the last couple of slides. And the right-hand side shows the similar representations for reverberated data. This is a parallel far-field data of the same clean recording that's shown on the left. So what you see here is, or what I would like to highlight here is essentially that in the autoregressive modeling framework, which relies on peaks, in this case in the spectrotemporal domain, one can try to see that the peaks are relatively well preserved even in the presence of reverberation, where in the MEL case, the reverberation has more of a smearing effect as seen in the spectrograms. Perhaps to go into more quantification of these sort of graphical illustrations is to do some sort of speech recognition experiments, which is what I'm going to discuss now. So the experiment that I discuss in this, we discuss in this paper is based on the reverb challenge data set. We have followed up these experiments on KIME and other data sets, part of which will be presented in the KIME workshop tomorrow. So in this set of experiments, we use the reverb challenge data set, which consists of Wall Street Journal CAM0 data set, which has two types of conditions for training. One is using simulated reverberation data, and other one using a clean condition training data. And the test data is either simulated or real reverberant environment. Two types of test set that were provided during the challenge. One was on the development set, and the other was on the evaluation set. And we use the CALDI toolkit hybrid modeling. We build the speech recognition engine either using the CALDI or using a Python framework, which is a wrapper for the CALDI. And we also perform multi-channel experiments, in which case we either use the recently proposed three-dimensional convolutional neural network front-end or use the beamforming based model. And we compare with MEL power spectrum as well as the power normalized capsule coefficients that were proposed in 2011, along with the proposed features. So the first question that we try to address in the experiments is, for this kind of reverberation task, what is the good acoustic model? So we freeze the language model and we try to play with different architectures of the neural network. We tried with a deep neural network, a LSTM model, a convolutional neural network, and a neural network of convolutions with a dropout. So as you see here for the ASR experiments, in terms of word error rate percentage, which is reported here, the convolutional neural network gives a significant advantage to other front ends. In particular, with the dropout, you get at least about 20% improvement from the feed-forward deep neural network architecture. So we try to use this convolutional neural network front end, which was initially trained only with the MEL spectrogram, now use it with the various feature models that I have described. In fact, the MEL spectrogram, the power normalized filter bank energies, and the multivariate autoregressive model. And what we see here is we get a good improvement even when this is the case when this is a multi-condition, meaning the training data was also on reverberation, the test data was also on reverberation, and you still get a gain of relatively 4 to 5% in these scenarios. In particular, what we were excited was in the evaluation set, which was much more of on the real data set, and the evaluation set, we had much more of an improvement for this kind of processing compared to the simulated data set in the first two columns of this table. So we move on to the multi-channel experiments, in which case the multi-channel experiments could be either be done by directly taking the spectrogram of all the subbands and trying to process them in parallel with a three-dimensional convolutional neural network architecture, or we could do a signal enhancement based on beamforming, combining all the multiple channels into a single enhanced channel and process them as a single channel speech recognition task. Note that both of them are already enhanced versions of the far field environment, and we also see that even with enhancements, even with simulated training of simulated training data which contains reverberations, the proposed approach gives good improvements over a MEL-based front end for the convolutional neural network-based acoustic model. Of course, as you can imagine that, when conditions are mismatched, meaning if I only train on the clean data, which is also a part of the challenge in 2016, if I train only on the clean portion of the data, then the improvements due to the autoregressive model are much more significant. You get relatively of the order of more than 10% improvements in these kind of scenarios where the trained data was clean, but the reverberated data was applied only on the test. So these sort of experiments kind of highlight that even with data augmentation, one could benefit some more based on multivariate autoregressive modeling framework. And of course, in the KIME and other evaluations, what we try to do is to combine the models from the MEL spectrogram as well as the MAR framework, and we get even further gains. So just to move on to the conclusions. So what I have spent the last 15 minutes of this talk on is to highlight that autoregressive modeling of subband envelopes is a good approach to proceed if you want to achieve some sort of robustness in far-field environments. The model that is proposed kind of extends the previous approaches on single band isolated modeling. Although I didn't put the results of this, what we found is that the isolated modeling sort of improves only on the clean condition training. On the multi-condition training, we couldn't see benefits for the isolated subband modeling, but the multi-band autoregressive modeling framework gave some important improvements, particularly by modeling the joint spectrotemporal plane. And we also saw that even with enhancement methods like beamforming in multi-channel scenarios, one could sort of get benefits additionally by using the autoregressive modeling framework. That's all I have for the talk. Thank you for your attention.
Let's thank the speaker.
Feature like main filter binding or PNCC. So I would like to say that it's also possible to compare with other similar other features which have similar principle of extracting temporal envelope, like the subband temporal envelope feature that we at Toshiba published last year in Interspeech. So just would like to bring your attention to this comparison.
Thank you. I haven't seen the paper or
I think eternal problem for our ASR and lot of speech modeling understanding. So TF plane, you exploiting it since quite some time is very interesting. But is there any other higher dimensional mapping that we can think of in which this kind of interference signals as well as noise or anything else is better separated? I mean, I'm sure it has drawn your attention sometime or the other.
Thank you. And project into a large number of two-dimensional filters which isolate the modulations in the spectral and the temporal domain. They call it the rate and scale representation. And this becomes a very high dimensional feature of the order of few thousand dimensions. The problems when we were trying to use the model in my past life were that the high dimensionality and in fact sparsity of the data causes lots of issues when we try to fit them into the conventional ASR style framework. So that causes issues when we try to model them, although we can see that some feature dimensions are much more robust. To learn a meaningful model with the limited amount of data was always challenging. But certainly it's worth a research direction if now with the current advancements with various modeling methods, modeling high dimensional data is not a taboo anymore.
Okay, we have time for last question.
In decoder and in various other places where you would automatically need to chunk, we don't take, I would believe that we don't take voice search or any other decisions based only on the current time frame or the last few time frames. You would rather chunk the data in some sort of buffer before you can detect the words or subwords or let us say even phrases and sentences. So there is anyway a buffering happening in addition to trying to model this for the ASR. So this adds the, let's say, the context information or the latency at the feature level itself. Yeah. So it wouldn't, let us say, the same window that you would apply for ASR could also be used for feature extraction in this case. For these experiments, since we didn't have those constraints, we used a 2-second window, but it's more robust than 2 seconds.
Okay. Let's thank the speaker.